the networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
Thank you so much, everybody, for coming to my talk. I know there's a bunch of other, very attractive options in the same time slot, so thank you very much for choosing me. So this is Beyond Sequential Consistency. So, my name's Chris Fretz. I'm part of the Bloomberg crowd. Obligatory comment. So I work within an organization called TickerPlant on a developer experience team, and we are hiring. So we have an open position that we can take externally. So if you like what you see, come talk to me. But cool. So starting out with an overview for this talk. The goal for this talk here is to discuss the different memory ordering models that are available in C++, along with the actual practical performance differences between those models. And that's what I see as being kind of the unique bit about this talk. There have been a bunch of talks that have been given over the years on this topic. I saw one at C++ Now a couple years back by Alex that was very, very good. But I had not previously seen a talk that would actually try to say, like, okay, so here are what the memory models are for, but like, what is the actual performance differential that we get out of using these things? I feel like that's kind of important because it's hard enough to write lock-free code in the first place. But if you're gonna reach for the less consistent models, it gets more difficult. I think that we should probably have an understanding of what are we actually going to get? What are we leaving on the table around these models? So that's the specific goal of this talk. We start with a quick introduction, defining terms and core concepts. I am very much hoping that someone who has never worked with lock-free programming before will still understand this talk and get stuff out of it. We then move on to considering specific implementations and different memory models. So this talk focuses on what I consider to be an elegant lock-free data structure. There's not necessarily many of them. They tend to get pretty complicated, but one that is very elegant and also happens to be extremely favorable for memory ordering optimization. So your mileage may vary in terms of what you'll see. We compare the relative performance of different memory models for this data structure. And we also consider some surprising outcomes where atomics are actually not even necessary. So that one's kind of fun. But cool. So before we get into the actual meat of this talk here, so this is an image that I had ChatGPT generate for me. I think that it's pretty true. So what I'm trying to get across with this image here is basically that lock-free code should not be the first thing that you reach for. It's hard to test, it's hard to maintain, it's hard to prove correctness on it, and it's not guaranteed to be faster. It may be faster. It could be that your use case is really well aligned and it will be faster. But most of the time when you're writing a lock-free algorithm, you're exchanging doing more work on average to have better progress guarantees. Just make sure that you benchmark, make sure that you really consider whether or not your use case needs it. And even if it is faster, there still is a question of does your application actually need that? Because it is going to be harder to maintain over time. So that's my little disclaimer. Now we can get into it. Obviously, I think that lock-free programming is very cool, but also having been in the experience of having written way too much of it and then being responsible for maintaining it, I just want to bring that up. But cool. So before we start here, we should probably define what do we actually mean by lock-free. Well, so colloquially, what people typically mean here is avoiding the use of mutexes and system calls. So specifically avoiding software locks. At the end of the day, if your program is actually going to do something useful and create value in the world, you're still going to have to synchronize. There still has to be a well-defined way that your threads interact. But what people usually mean by lock-free programming is that we do not use software locks. So we instead depend on hardware intrinsics that guarantee that certain operations are uninterruptible or atomic. And more formally, the term lock-free is about progress guarantees. So specifically, the more formal guarantee is that with a lock-free algorithm, at least one thread in the program is always making progress. And specifically where this comes from is that if you are a thread and you're trying to get something done and you're not able to and you have to back off, it necessarily means that somebody else did get something done. And so you can contrast that to like a traditional blocking algorithm where the OS might put everybody to sleep and there's no specific guarantees about when anyone will make progress. But cool. So getting into the C++ memory model specifically, starting in C++11, we gained a formally defined memory and model that includes multiple different memory orderings. And so specifically, we have relaxed, we have acquire, we have release, we have acquire release, and we have sequentially consistent. For those in the audience that know the space, there is a sixth one here that we don't really like to talk about very much called consume. You can ignore it. It's been deprecated in 26 and is becoming equivalent to acquire. My understanding is that it never really worked the way that people wanted it to. So this at a high level is what we have. And acquire release and acquire release are actually, they're kind of the same sort of thing. And so essentially we have three options here. We have sequentially consistent, we have acquire release, and we have relaxed. And so it kind of begs the question of like, why do we have all of these different orderings? Like, what is this for? Like, this seems like a lot of complexity. And so like, why are we bothering with this? Well, so on a modern symmetric multiprocessing machine, which is to say any computer that you've used for like the last 25 years, all cores are interacting with memory simultaneously. Each core in the CPU has its own cache, meaning that different cores within the CPU may have independent copies of the same data. And if you have multiple cores that potentially have multiple copies of the same data, and they're all interacting with memory and changing it at the same time, it becomes a question of like, who sees what and at what time? Like, say that you had, 4 cores, you had 4 threads, you had 2 threads working on variables X and Y, and then you have 2 other threads. And the question is, like, from the perspective of threads 3 and 4, what do they see when it comes to the changes for X and Y? Like, do they even see the same thing? Like, do we even have a guarantee of coherency? And so this is kind of an interesting question. And do different cores even agree on the relative ordering of events? And this is not guaranteed by default. And so the different orderings of the C++ memory model give fine-grained control over this and kind of bring order to the otherwise chaos that you would be exposed to. So the way that you can think about this here is that C++ defines an abstract model with several different available orderings that give different abstract guarantees about how different threads and cores will observe events. And then it's up to vendor and library authors to actually leverage the hardware and platform-specific intrinsics to actually implement and uphold this model. So C++ gives abstract guarantee, and then it's up to GCC or Clang or MSVC or what have you to actually then implement that using the hardware intrinsics for that platform. But cool. So what this kind of gets down to at the end of the day, and something that we don't really have to think about very much most of the time, because modern toolchains do an exceptionally good job of insulating us from it most of the time, is that modern machines and toolchains can reorder the execution of your code at build, link, and runtime. They can reorder it essentially anywhere. And in general within C++, the optimizer can decide to do essentially whatever it wants, as long as it conforms to the as-if rule, which is to say that the program that it emits runs as if it was the program that you wrote. Within the requirements of the C++ standard. But there's a lot of freedom here. I mean, obviously so. If anyone has ever benchmarked the difference between an optimized binary versus a debug binary, it's astounding how much actually happens in the optimization pathway. But so the toolchain can decide to reorder your operations. The CPU pipeline may actually decide to reorder instructions based on runtime data dependencies. So like when the pipeline is actually decoding instructions and deciding when to dispatch them, it's actually like dynamically inspecting data dependencies between instructions and may decide to run them in different orders. And the cache coherency protocol itself, which is to say the memory subsystem of the chip, may also cause loads and stores to be observed in different orders by different threads and cores. And so independent of everything else, the memory subsystem itself may also cause runtime ordering from the perspective of an individual core to violate common sense causality from the perspective of the programmer. And so this is something that you have to be kind of careful with, obviously. And so memory fences or memory barriers are the lowest order primitive that can be used to constrain these reorderings. And so there's multiple types of fences. There's the concept of a compiler fence. I think we get to a point in this talk, yes we do, where we actually have one of these. So this would be what appears to be a function call in your source code that exists purely for the build chain. It does not emit instructions, but it prevents the tool chain itself from reordering operations across that barrier. There's also a runtime fence. And these are actually like runtime opcodes, like actually dedicated assembly instructions that the tool chain emits that will constrain the CPU pipeline and memory subsystem. So you have both the ability to basically pin down the tool chain and say you can't reorder, but you also have the ability to pin down the runtime environment and say the same. And so you can kind of think of there as being two axes here. So we have the compiler fence and the runtime fence, but then within that, we also have additional breakdowns on store fences versus load fences versus combined or full fences. And so this is specifically constrains what types of operations can be reordered across the fence. And so this gives you a lot of flexibility, and at the end of the day, this is what the tool chain itself actually uses to implement the abstract model that C++ guarantees that you have. And so at a high level, that's kind of what these things are. But cool, so we can get into the actual memory models themselves here. And so this first one here, so this is another GPT image. You can see we have like a very orderly train platform here. We have people walking in a nice, well, maybe not quite single file, but sort of line to get onto their train. Like, you know, it looks like hopefully this thing is arriving at a reasonable time. I don't know why the conductor is standing on the tracks over here, but outside of that, it seems like we have a pretty orderly station here. And so starting first with sequential consistency. So the guarantee from sequential consistency is that there exists a total ordering of all sequentially consistent operations that all threads agree upon. Transitive visibility of operations is preserved, which is to say that basically your program will appear to uphold expected causal relationships around sequentially consistent operations for all threads. For sequentially consistent operations, no thread can see anything that appears like logically incoherent with any other thread. This is the default behavior. So there's this saying in C++ that all defaults are wrong. I think this is a case where we actually have a reasonable default, which is nice. But the problem is that it is, of course, also the slowest behavior. So like basically the abstract machine is taking the most kind of conservative option by default. But as we'll get into it, it is actually quite slow. And so to give a specific example here, so in this program, we have 3 atomic integers at global scope. They all get initialized to 0. Inside of the main function here, so we have a vector of jthread. If people are not familiar with jthread, it's a joinable thread. Like basically the idea is that when you destroy a jthread, it will implicitly join with the thread that it's managing. And so we have a vector of threads here. We place 3 lambdas into it, so that's going to fire up 3 threads in the background. We're then going to go out of scope for main. It's going to try to destroy the vector, which is going to try to destroy the threads, which is going to join with each of these threads and make sure that they exit before the program completes. And so in this particular example here, so you can see we have 3 different threads that are doing 3 different, ordering of increments here. They are all using the pre-increment operator. Like I said, sequential consistency is the default behavior, which means that if you use pre-increment, you are implicitly asking for sequential consistency. So with the way that we've written this program here, we have not put any constraints on what the actual runtime ordering of this will be. The operating system could decide to schedule these threads in whatever order it cares to. There are no guarantees from that whatsoever. And when these things are running, it could decide to preempt these threads at arbitrary points. We have put nothing in place that would guarantee what the runtime ordering would be. The guarantee that we do have, though, is that whatever the ordering actually ends up being at runtime, all threads will agree on what the increments were, like what the total ordering of all the increments were. And so if it ends up being, A, then C, then B, then B, then A, or some crazy ordering, like all of the threads, there is no thread in this program that could see a different ordering of those events. And so that is what the specific guarantee is around sequential consistency. The next one that we have here is obviously acquire release. So I am not sure that GPT really understood what I was trying to do here. Like I wanted to put multiple hands on this clock to show that people don't necessarily agree about what time it is anymore. I don't know what's going on with that clock, but you can see that this is, starting to look a little bit less coherent than it originally was. The people look a little bit more hurried. There's weird stuff starting to happen. And so for the acquire release model here, the way that you can think about this is that acquire release usage on a specific atomic variable sets up a synchronization point between different threads. This is a lot of text, but I think it does a really good job of explaining it. So if thread A stores into variable X with release ordering, and thread B loads from that variable with acquire ordering, it is guaranteed that B can see all of the transitive stores that were visible to A at the time that it made the store into X. And so like if A stores 5 into X, and then B pulls loads with acquire, like it stores it with release ordering, and then B loads with acquire ordering and gets that 5, it's guaranteed that everything that thread A could see at the time it stored that 5 into X is now also visible to B. It is said that in this case, thread B synchronizes with thread A, but there are no guarantees that are given for threads that do not synchronize in this way. And so, like, yeah, I mean, this is an example of it. But the way that I think about this here is almost that acquire release kind of allows you to set up for a set of threads synchronizing on a particular variable. It gives you a way to kind of like almost hand off sequential consistency. Like it gives you the ability to reason in a common sense fashion between the set of threads that synchronize in this way. And so as another example program here, we have 2 booleans at global scope. One of them is an atomic boolean, one of them is a non-atomic boolean. Ignore the fact that I did not use universal initialization for this first one for whatever reason. That's not intentional. But yeah, we have 2 booleans at global scope. And inside of the producer thread, we store true into the non-atomic variable and then store true into the atomic variable with release ordering. In the consumer thread, so yeah, these are 2 different threads here is the idea. In consumer thread, we load off of atomic with acquire ordering, and we then assert non-atomic. And so the crucial realization here is that we are not guaranteed to make it into the body of this if condition. Again, the operating system might decide to schedule consumer thread before it schedules producer thread, in which case this will load false and we just won't do anything. But the point is that if we make it into the branch of this if condition, like if that load acquire loads true out of the atomic, that means that this non-atomic has happened before that. Like there is an implicit fence here that sets up a happens before relationship between these 2 stores. And so if this load loads true, it is guaranteed that this assertion will pass. And so, you can imagine in this particular case here, I've just taken 2 atomic booleans. You could have a much more complex case where you're calling into an object that has a member function that has all sorts of observable side effects across the program. The guarantee here is that everything transitively that had happened, that producer thread could see when this store happened, is now going to be visible to the thread down here. So that hopefully gives some kind of intuitive understanding of how this is meant to be used. But cool. Oh, that's right. And then I'm also trying to show I was talking about the implicit fences here. So the idea here is that there is an implicit fence in both of these cases. So this store into non-atomic cannot be reordered below this store into atomic. And also this load off of non-atomic cannot be reordered above this load. So it again is just kind of getting more into specifics about how this is implemented. But cool. And then finally we have the relaxed case. It's total chaos. There is not even a platform anymore. I don't know why the trains have faces. I did not ask for that. But it's just, yeah, it's very bizarre. Nobody knows what's going on. And this is, hopefully helping you build some kind of intuitive feel for what is going on here. So with relaxed ordering, it only guarantees atomicity, which is to say that no thread can see a partial write. So you do still have the guarantee that from the perspective of any thread, it either happened or it didn't. It's not possible to see a partial write. And also this thing called modification order. So I was not actually familiar with this before I started researching for this talk. But the idea with modification order is that you still have a guarantee of a total ordering of writes to that one location in memory. You do not have any ability to reason about the ordering of events between different variables or different locations in memory. But modification order says that for that one spot in memory, all of the threads will still agree on the order of things that happen to that one location in memory, essentially. So like you can't see things in incoherent orders for that single location in memory. But yeah, there are no guarantees whatsoever in terms of the ordering or visibility with other reads or writes, and it establishes neither a runtime fence nor a compiler barrier. And so it can be reordered arbitrarily at compile and runtime. And so to take another specific example here, we again have 2 atomic integers at global scope, and we have 2 threads here. And a valid output of this program, it's not guaranteed to print this, but a valid output from this program is that both threads print 42. And like, how could that possibly be true? Because 42 doesn't even show up until halfway through the execution of thread B. But what could happen is that the compiler, for its own compiler reasons, decides like, I don't really want to do that. Like you wrote some stupid thing. I don't want to write what you wrote. What I would prefer to do is that. I would prefer to hoist the store into 2 above the load from 1. And then the operating system, again, there's never any guarantees about how exactly your threads are going to get scheduled. The operating system could decide like, well, I would really prefer to run thread B before I run thread A. And so the specific ordering here is that we store 42 into 2. We then immediately get put to sleep. Thread A starts up. We then load 42 out of 2. We store it back to 1. And then thread B wakes up, loads 42 from 1. And now both threads think that the value is 42. And so probably it was not intuitively obvious to anyone that that was a valid output from this program, but it is. And so hopefully that gives some kind of intuitive sense of like how little ability you really have to reason about relaxed operations. And so like you really can only use these things in a situation where you know that you really do not care about ordering whatsoever. So that's relaxed ordering. But cool. Yeah, so relaxed gives the implementation total freedom to reorder at any or multiple levels. It gives the programmer very little ability to reason about causal relationships, but hey, it's fast. So that's nice. Cool. So now that we've defined the actual memory orderings in the standard itself, we can talk about like a actual practical use case for this. So I was saying before that I think this is the prototypical example that is extraordinarily useful, elegant, and fast. And that is, of course, a lock-free ring buffer. Lock-free ring buffer uses a circular buffer of memory along with atomic counters to move data between threads. The basic use case for a data structure like this is single producer, single consumer. It can be trivially extended to single producer, multiple consumer. You can even do multiple producer. It gets more complicated. But at a very high level, you can kind of imagine something that looks like this. I will come back to this slide. But the basic idea here is that here's your consumer, here's your producer. The data records are what's between them, and like stuff just kind of moves from left to right here, essentially. And so I think the easiest way to explain this is the concept of the infinite array. You can imagine that if you had infinite memory, you could trivially implement a queue using only 2 atomic counters, a producer index and a consumer index. And queues would be performed by copying data into the array and just incrementing the producer index. And dequeues would be performed by copying data out of the array and incrementing the consumer index. And crucially, indexes increase monotonically, which is to say, like, numbers never go down. They only go up. And this is actually a really strong guarantee. You can get a lot of really nice things out of this. But so this is coming back to what I was saying before here. So when the producer writes its next record, so its next record will get written in here, it will copy the data in, and it will then move beyond that. And the consumer then knows that there is data there because of the fact that the producer has moved forward. So obviously, in practice, we only have finite memory, like wouldn't it be nice? But the design can be trivially adapted. So our real-world queue will still maintain 2 atomic counters, the producer index and the consumer index. And the counters are still logically indexes into the infinite array. So they still go up forever. They never decrease. But we use modular arithmetic to map them into a finite buffer. And that buffer is used circularly, wrapping back around from the beginning to the end. I don't like this diagram very much, but other people have told me that they do. This is another GPT thing. So basically, I'm trying to show that this is circular here. So like the memory gets reused repeatedly, just kind of running around in a circle. I have a better one though. So you can imagine here, this is the initial state of our queue. So our consumer index is 0, our producer index is 0. The producer can then run ahead and create 3 records. The consumer can now see that there are 3 records to consume. And the 2 things will kind of chase each other and run off to the right. And then the interesting case here is the wraparound case where the producer then has to go back to the beginning. And so in this case here, the consumer can still tell, like you can see producer index is still 12. We are now on index 2 in the actual memory, finite memory that we have access to, but the logical index for the producer is still 12. And so the consumer can always see how much data is in the queue by just diffing these 2 pointers, essentially. In terms of a concrete implementation, we are going to start with the simplest conceivable ring buffer here. So we're just moving 64-bit integers. So we have a producer thread here, and we have a consumer thread. The idea is these would be run on different threads. We have a counter. We just spin up to 10 billion on both of the threads. We just push the counter into the queue and then increment for the next one. And then the consumer crucially actually asserts that this stuff, like it also has a counter and it keeps track of that stuff as well, so that we can assert that things come out in the right order. Like the idea here is to guarantee that like we are actually benchmarking what we think we are, and we do not have a bug here, so everything comes out in the order that it was put in. So at a high level, kind of API level here, we just have push and pop, and they do what you would expect. In terms of the implementation of the class here, so obviously in real code, this would be a class template, but this is slide code and I'm trying to make it simple. So we have our capacity up here. So I've chosen the 15th power of 2. In my testing on the hardware that I was using, that was just experimentally the best value for this queue. It could be anything. It's easier if it's a power of 2, but it could be anything. And then in terms of data records here, so we have our next producer record, our next consumer record, and then our actual data array here. And then so we have our push and pop functions. They work the way you would expect. And we have some helper functions here that we'll get into. But at a high level, this is basically the entire definition of the class. In terms of the implementation here, so for the push function, we take the 64-bit int that we want to push. We then have this like back off here essentially. So the size function you can see down here, this is implemented just as next producer record minus next consumer record. The reason that it is this simple is because this is a single producer, single consumer. Like in this case here, when I'm in the push function, I am the producer, and so I know that this value can't change. It's only the consumer that can, and so that's why size is this trivial to implement. And so while size is equal to the capacity, the queue is full, and so we sleep. And then once there is data space available in the queue, our map index function here, we just mod the index into a capacity. Since we're using a power of 2 here, the compiler will convert this into a bit mask for us, but the code is more obvious. We just copy the record in, and then we just move our producer record forward. And the pop function is basically just the same thing. Like you can see like how similar these functions are. The difference is that the predicate here is while size is now 0, which is to say that while there is nothing in the queue, we sleep. Otherwise, we pull stuff out of the queue and increment the consumer record. And then in sleep here, you can see this is just a very basic, just like spin lock, essentially. Like it just tries to spin 16 times before it starts going to sleep. That is basically the whole thing. In terms of the driver program for this queue, we have our print stats function up here, which just like sleeps for a second and just checks the diff essentially. So this is just continuously calculating the velocity that the queue is moving at by just looking at the producer and consumer records. And then in the main function, we just make these things and just run the threads essentially. And like this is real code. Like I've spread it across like 5 different slides, but I think this is basically everything. And if you do this, this is what you get. So I ran this for 10 minutes, which was total overkill, but that's what I did. And so you can see we're moving at something like 10 million records per second for this queue that just has 2 threads pushing integers through. I don't know if people have spent very much time benchmarking lock-free queues. Like this 10 million records per second might sound really fast, but it's actually really not. It's actually pretty terrible. The chip that I was benchmarking on was running at 2.6 gigahertz. It was like a Xeon, like Intel server class chip. And so at 10 million records per second, it means that we're spending something like 260 cycles per record. And like our queue is doing nothing. Like it's not doing anything at all. Like we're pulling these things out of the queue and we're asserting them, and it's moving integers. Like this should be the fastest possible case. Like we should be able to go a lot faster here, and yet we can't. And so it begs the question of what gives. And so Compiler Explorer is so useful. It makes this so easy to do. So here is our push function, and here we actually have a disassembly of it on the right. And so the exact details here are not like super duper important. We have our index loads up here. This is when we actually get the queue size and check if there's capacity. If there is, we then jump to the production. Otherwise, we go into our sleep back off. And the production is super simple. With the way this code is written right now, we end up loading the producer record twice. But so we reload the producer index, we mask it to like do that modular arithmetic, and then we just store it in the queue and increment. And if we look at the consumer, it's exactly the same thing. So our comparison here has now turned to equality because we're checking if it's empty. We're checking if there is stuff in the queue. But otherwise, the production looks exactly the same. So we load the consumer index this time, we mask it, we move the thing out of the queue, and then we increment our consumer pointer. And then because everything gets completely inlined, this is our assertion check here. So like JNE is when the assertion fails. And so the thing here is that like the only potential bottleneck in this assembly is the lock add instruction. Like there's nothing interesting going on here. Like we have adds, we have moves, we have comparisons, we have conditional branching. But like, like all of this stuff is cheap except for this lock add. Like this is the only thing that's really very interesting in this assembly. And so this lock add instruction is a read, modify, write operation, which is to say, like we're trying to do a pre-increment here. And so from the perspective of the hardware, it needs to load the current value of the record. It needs to then increment it, and then it needs to flush it back to memory. And because we have this lock prefix here, all of this happens in a single atomic step from the perspective of the rest of the hardware. And so, it's a read, modify, write instruction that issues a full memory fence. And like, do we really need this? Like, we've implicitly requested this because we've done plus plus and sequential consistency is the default behavior, but do we really need this? Okay, so I already said that. But yeah, we're implicitly requesting the fetch add here and full sequential consistency. But the producer and the consumer are individually single-threaded. Like our access pattern does not require sequential consistency. There is no contention on this index. They're incremented one thread at a time. And so we don't need either of these things. We can avoid both. And so a very trivial reorganization of this program here is that so at this point now, we're no longer using the nice operators. We're now issuing the loads and stores manually. But so we load acquire on the producer record up here, and we then store release when we actually update it into the queue. And you can see we also, on the consumer record here, we load acquire off of that. And then on the consumer side, it's the same thing. We load acquire the consumer record, store release into the consumer record, and then crucially, we load acquire off of the producer record here. And so this is, you can see this is almost exactly the same code we had before. We've just changed the plus pluses into loads and stores. And if we take a look at the assembly here, so the compiler gets really aggressive after we do this, and things have been reordered a lot. But logically, we have our consumer index load, our producer index load, we do our capacity check. And then in the production here, what is interesting now is that you can see, so this is when we're doing the masking, this is when we store into the array. We then increment the producer record, increment the current record, and then just update the producer index. And what's interesting here is you can see our lock prefix has disappeared. Like if you look through this code, there's actually no lock prefixes anywhere in this code at this point now. And if you do this, this is what you find. Is that like literally by making those 4 or 8 line changes or whatever it was, we go from roughly 10 million operations per second up to about 175 million. So we've had like a 17x improvement off of just moving off of sequential consistency to acquire release. And it's obvious to see why. Like there's literally no atomic operations in this code at this point now, which is really exciting. And so yeah, our new code has literally 0 atomic instructions or fences on x86, which is awesome. At 2.6 gigahertz, 170 million records per second is about 15 cycles per record. So we're really going a lot faster here. It's actually so good that when I originally saw this, I'm like, is this too good? But like the test machine here has 32 kilobytes of L1 cache and a megabyte of L2 cache. And our queue only contains integers. And so the whole thing fits into L2 and about an eighth of it fits into L1. And I mean, additionally, like I've literally disassembled this stuff and like inspected it. Like I know that I'm not benchmarking a busy loop here. So this queue is too small to be realistic, but it shows what the hardware is actually capable of. Can we still go faster? Like, why not? Like, this is C++. We always want to go faster. So the next observation here, so this is another GPT thing. But so we have a brother and a sister here that want to do different things. The brother wants to do his hair. I mean, his hair actually already looks pretty good. But he wants to do his hair. And the sister wants to brush her teeth. Totally unrelated things, but there's only one bathroom. And they can't be in the bathroom at the same time. And so we have the tagline here, like separate routines, shared resource, false sharing slows everyone. And so we still have contention in this program. But like where? Like this is lock-free code. Like what could we possibly be contending on here? I mean, we literally just looked at this disassembly and saw that there were no atomic operations in here at all. Like what could we be contending on? Well, so the thing that's interesting here is that the way that we have declared this queue here, our producer record and consumer record are atomic integers. They're atomic size t's, and so they're both going to be They're both going to be 8 bytes on my platform, and they're right next to each other. And so like they are almost guaranteed to fall on the same cache line. And like normally this is a good thing because like it means we have very good data locality. Like it'll be very easy for the caching subsystem to pull all of this into memory. But the problem is in this case here, our current memory layout packs them onto the same cache line. And the problem is that different cores will fight to modify this same line concurrently. So on basically any system I've ever worked with, a cache line is the minimum granularity of memory that you can really work with. And so like the problem here is that at least on x86, there's this thing called the messy cache protocol. It stands for modified, exclusive, shared, and invalid. It's the protocol that the caching subsystem uses to actually keep the cache lines coherent across different processors. And so the problem here is that the producer and the consumer are both trying to update these records simultaneously, and they are on the same cache line. And so the problem is that when the producer goes to increment its pointer, it is going to have to invalidate the copy of the cache line that the consumer has, and vice versa. So like, producer is going to invalidate consumer. Consumer is then immediately going to have to refetch the line from the producer core and then invalidate the producer. And like this is literally going to keep happening with these things, just having to bounce this cache line back and forth. So there is a thing in standard C++ called hardware destructive interference size. And I actually already heard this mentioned at this conference, which is very cool. I had never heard this come up in a conference talk before. But so there is a thing in standard C++ to fix this. This is in the header new, if I'm not mistaken. But this exists to solve this problem. And so basically, this will end up being the size of a cache line. On every x86 chip I've ever worked with, cache lines are 64 bytes wide. So what you can do here is we can actually have another const expr size t up here, just load hardware destructive interference size, and then I can use a line as to actually align all of these things to a cache line boundary. And so at this point now, with the fact that my cache line size is 64 bytes, that essentially means that each one of these things is going to require 64 bytes. So we waste a little bit of space. But what's nice is that these things are now guaranteed to have their own individual cache lines. And so if we literally just add these align as specifiers, this is what we then get. And so this yellow one up here is the aligned version of this. And you can see that we still get like another 20, 30% off of just aligning these things. And one other thing that I thought was actually very cool is you can see how stable it's gotten. Like the previous one was really bouncing all over the place. And this one has really gotten quite stable. And so this is very cool. So yeah, from where we started from here, there is a huge difference, including the alignment. It's almost 20x using different memory orderings. But again, this queue is too trivial to be realistic. And so how can we make this benchmark more realistic? The most obvious thing that comes to mind here is to see how performance trends as the data gets larger. And so here right now, so we have, these names are probably not the best, but so this big fast queue. So the fast queue, if we go back to here, so I've been using the terms naive, relaxed, and fast. And so fast is the one that uses the acquire release and is aligned. And then naive is the initial sequential consistency version. And so these are both with 64-byte records. And so we can see at 64-byte records, the difference is still 10 million to 7 million. So we're still getting 7x. If we then go to 128, you can see that from the perspective of sequential consistency, it's exactly the same. But we're going from like 10 to 50 million. And then even at 256 bytes, we still have a 100% improvement. Like sequential consistency is still stuck at the same spot. And our acquire release is up at 20 million. We have to go to a full kilobyte before the cost of copying the data actually becomes more expensive than the intrinsic cost of the memory ordering. And even in this case, it's hard to see on this graph because of like the size of the axes, but this is still 3 million versus 4 million. So we still get like a 25-30% improvement even at a full kilobyte. And so like the performance diff actually is durable in this case. You have to go to a full kilobyte before the copy is the dominating factor. And even in this case, we still save something like 25%. But now, kind of an interesting thought here is that with this acquire release optimization, our code now issues 0 runtime memory fences. And so like, do we actually even need stood atomic here? Like, what is it doing for us? What does it give us? What happens if we drop it? Like it's, what could possibly go wrong? And so here we have our undefined behavior queue. And so like this is bad code, like do not write this code. But it looks largely the same as before. I've kind of, gotten rid of the details down there just because again, it's a single plot. But you can see we're doing everybody's favorite thing here and synchronizing via volatile. Yeah, so this is basically the same, it's just we've dropped the atomics. And if we look at the implementation of this, again, it looks about the same. I've added this atomic signal fence, so this is a compiler barrier here. Yeah, like, I don't know that this is actually really necessary. These also probably don't need to be volatile. Like, really all that I'm doing here is that what I'm doing is already wrong and broken and don't do this. But I am trying to encourage the compiler to not break my code. And so that's why this will not issue runtime operations. This is purely for the tool chain. And writing this code, I also found out that pre-increment and post-increment are deprecated on volatile. I actually didn't know that, but that's why it's written like this. And the consumer is exactly the same. Like it's exactly as it was before. We just now are not using any of the atomics. And so if we do this, what we find is this. Like it does actually work, and the performance is essentially identical. If we do the disassembly, we find that it yields essentially the same code gen. And so like, have we shown that stood atomic is unnecessary? Like, have we shown that the standard is wasting its time by defining all of this stuff? Well, so what happens if we take this exact same program and run it on the laptop that I'm currently presenting from right now? Once we do that, what we find is that the second that we start it, it immediately explodes and dies. And so it's nice to know that our assertions work. It was actually funny, when I was going through and testing this, this was actually the first time that my assertion failed. So it's nice to know that it actually is working. But so what happened here essentially? Like, what went wrong? Why does this work on x86 64 but not on ARM 64? And it comes down to platform guarantees. So from the Intel x86 64 architecture specification, and this is actually a link to like the IA64 processor manual, neither loads nor stores are reordered with like operations. Stores are not reordered with earlier loads. Loads may be reordered with stores to different locations, but stores are transitively visible, and stores are seen in a consistent order by other processors. Like, this is a lot of text, but what this ends up essentially meaning is that x86 just natively implements acquire release. And so the reason that us using acquire release at the C++ source level does not emit any fences at all in the actual assembly is because on x86 it's not needed. And so another way that this is sometimes said is that on x86 you are always paying for acquire release all of the time, regardless of whether or not you ask for it. And so Yeah, I remember at a previous conference, somebody took issue with the way that I said this, essentially free. Again, you're paying for it all of the time. But this is not true on more weakly ordered platforms like ARM and PowerPC. ARM actually requires an explicit load, acquire, or store release opcode to accomplish the same. And if we actually go and compile this same program on ARM, you'll see that we actually do get these. So this STLR function here, this is a store release, and then LDAR down here, this is load acquire. And so again, we've just written the same C++ source code, but the implementation knows that on that platform, we need explicit runtime fences to get this same guarantee. And so, like, this is obviously what we're missing here are the fence instructions, but like, what does this actually matter? Like, what is the problem here? What are the fences preventing? And so, like, yeah, why do we actually need the fences? Well, the first thing to think about here is like, what ordering requirements do we actually have in this program? Does it matter if the producer reads the consumer's operations out of order? Like, what would that even mean? Like, from the producer's perspective, the consumer does one thing. Like, as long as in the consumer thread itself, it issues the read out of the queue before it issues the increment for the index, that it's fine. Like, from the producer's perspective, the consumer does one thing, which is that it increments its index. And so it's not really possible for the producer to read the consumer's operations out of order. But does it matter if the consumers read the producer's operations out of order? And this is fatal. This is the problem. So specifically right down here, you can see from the consumer's perspective, like the producer does two observable things. It stores a record into the data array, and it then increments its index here. And so the problem is that without having the release fence here, it is entirely possible that the toolchain or the runtime environment or whatever can choose to swap the order of these two things. And so the problem is, this is not the best visualization, but what I'm trying to get across here is that like our queue is broken. Like from the perspective of the consumer, like it sees the producer move forward before it sees the updates into the queue. And so what we actually find if we go back and look at that assertion failure, I can't remember if it's on the slide or not. Oh, it's not. All right, well, so what you'll actually find when you do this, if you actually print the values here, the difference between the expected value versus the seen value is always a multiple of the queue size. And the reason for this, if we go back here, is, without the release fence on the producer side and the acquire fence on the consumer side, the consumer can see the producer move forward before its queue updates are visible. The consumer then reads junk from the previous iteration, and stood atomic ensures that we always get the correct behavior on all platforms. So like on x86, it makes it as fast as it possibly can be by just not emitting any instructions at all. But on ARM, it still gives us a program that actually works. And so like, this is very nice. And so if you go and benchmark this on ARM, this is again on my laptop. That was the only ARM chip that I had access to. So it's not apples to apples with the server class chip that I'm benchmarking against, which is why I'm not showing them together. But on ARM here, so this is again at 64 bytes. So this is our sequential consistency. This is our unaligned, and this is the fully optimized version. And I guess I only did 64 bytes on this slide. But you can see that from the sequential consistency to like the optimized relaxed, we're still getting something like more than 100% improvement. So it makes a massive difference on ARM as well. And so from a perspective of conclusions here, using the right model for the job can make a massive difference. Performance can be hard to reason about. Sometimes it yields surprises. The standard memory model does an excellent job of ensuring that you can't write better yourself. Like, I started out with this talk by trying to write better myself. The way that I actually started writing this talk originally was that I knew that you could write that undefined behavior queue and that it would work. And so I went into this talk being like, can I write something better than the STL? And the answer is no. And so it does a very good job. Relaxed atomics can be very difficult to reason about, but it can be worth it in the right context. And I have bonus material. I've gone a bit faster because nobody asked any questions. I have bonus material that I can get to, but this is the end of the official material here. But cool. Thank you. So I can take questions now, or I can go into bonus material. What do people want to do? Okay, all right, cool. So then this is a really interesting one here. So the original version of this talk was 90 minutes long, and so this was originally part of one coherent flow. It's been broken up a little bit here. But there's another optimization that we can make here. So when I was researching for this talk, I encountered a paper here. I'll send the slides out afterwards. People can load this up. But a white paper published in 2009. And this suggests further optimizing the cache performance with the introduction of cached indexes for both the producer and the consumer. And I'll get to what I mean by that. So it adds an additional cache line aligned index for both the producer and the consumer that holds a previous snapshot of the opposite index. And so these cached copies are only updated when the producer or the consumer would otherwise need to sleep. And so yeah, this resolves the final remaining cache, a cause of cache misses for this simple queue. So here's what I mean. So I realized after I wrote this slide that this consumer cache and producer cache, these don't even need to be atomic because these are only operated by a single thread. But the idea here, we still have our next producer record and our next consumer record. But then we also have this producer-consumer cache and consumer-producer cache. And so the idea is that this one right here, this is exclusively used by the producer, and it holds a cache of what the consumer record's value was the last time that it looked at it. And this is this is the same here, where the consumer holds a cache of the producer value. And this is why I say these don't even need to be atomic, because this is exclusively used by the producer, and this is exclusively used by the consumer. And the reason that this is valuable, so we solved this problem of false sharing before, but we actually still have a cache problem here, which is that like these two indexes, excuse me, these two indexes are constantly mutating. And so the problem is that we still, because of that messy cache protocol, we still have this problem of every time that they're now on different cache lines, but every time that the producer increments its index, it is going to invalidate the copy of its cache line on the consumer core, and vice versa. Like any time that a core modifies a cache line, it has to invalidate all of the other copies that other cores have. And so the problem is that basically every time the consumer goes to actually read the producer index and vice versa, they're gonna take a cache miss because it was like literally just invalidated. And so the idea with this is to have like a local cache line on each core that you only update when you physically have to. And so like the producer, when it starts, will snapshot the consumer record's value. I mean, at the very beginning, it'll snapshot 0 and it'll have to immediately update it again. But the consumer would snapshot 0 and have to immediately update it. But the point is that you only update these things when you run out of space in the queue. And so what we get, if we benchmark the original queue that does not do this, you can see that we have only 6% L1 decache misses. This is actually less than I was expecting to see. But we also have about 32% of last level cache misses. And so when we do miss an L1, we then go on and miss about a third of the time. And so if we look at the optimized version here, this goes from being we miss about a third of the time to essentially never. The L1 decache accesses only go down by about 1%, which is less than I was expecting to see. But the difference on like last level cache misses changes dramatically. And if you look at the total number of L1 decache loads up here, you can see that we were doing 29 billion. We're now doing 87 billion. And the two things ran for exactly the same amount of time. And so like performance has really improved dramatically here. And this is what you actually get out of this. I remember when I went and benchmarked this, like I almost choked on my food because this is just like so outrageous. If you actually run the numbers for this, it means that at this point now we're managing to move these queues in move these records in something like 4 to 5 cycles, which is insanity. Like to be honest, I don't know if it would be possible to build a real-world program that could actually use this performance, because when you're going this fast, if you do anything at all, it's going to be a bottleneck. But this is nuts. Like I remember when I originally benchmarked this, I couldn't even believe it. And so we should probably do the same thing where we see how it kind of trends as the data sizes get larger. And so at 64 bytes here, you can see it's from 75 to 115 million. At 128, it goes from like 50 to like 70. it decays quickly is what you end up finding. As you increase the size of the records that you're moving through, this performance this differential is less and less significant. But a real world use case for this would potentially be passing pointers. Now again, in a real world application, there's just gonna be more cache noise going on. And so I don't know if you would ever actually see this, but it again shows what the hardware is actually physically capable of. And so yeah, for small queue sizes specifically, the optimization makes a massive difference. Our queue is only passing integers. A real world use case would be pointers. The question then comes up, like, where do I get these pointers? Like, how do I make sure that the allocator is not slower than my queue? It does decay as the data sizes get large, and it never seems to perform noticeably worse. So one other thing that I thought was interesting is that this optimization does not appear to be implemented by either Folly or Boost. These are links over to the single producer implementation, single producer, single consumer implementation for both. That again could be because they did the research and they found that for real world applications this doesn't make a difference. But I did think it was interesting because as far as I can tell, it never seems to do worse. It's just that at very small data sizes it does like substantially better. But yeah. I have more things here that got into like a multi-consumer queue. I don't have enough time to get into it. I've only got 5 minutes left, so I think I will call it there. But cool, thank you.
Is this mic on?
There you go.
Two questions. One is, so on slide 16, you had the concept that all transitive stores would like,
wait for it. There you go.
Yeah. So where was it? Yeah, all transitive stores. It's guaranteed that B can see all transitive stores that are visible to A. How do you actually define transitive stores? So you do mean atomic and non-atomic stores, like anything in memory. But what does transitive exactly mean here? That's like really difficult to like.
Maybe I chose a bad word here. Like basically what I mean is just that you can see the whole history of the program as it was visible to that thread at that time, essentially. Like what I'm trying to get across here is that it's not just atomic writes and stuff like that. Like and I tried to use the example of like, say that you have an object that has a member function that has a bunch of observable side effects. Like all of those side effects are going to be included.
So anything that modifies memory above the atomic operation that could be somehow observed below it?
Yes, exactly.
All right, cool, thanks. That clarifies it. And the second question is, so you mentioned there's two kinds of fences on the hardware side. Well, actually, there's two kinds of fences. One is the one that affects the tool chain, the compiler optimizations, and the other one that affects the hardware.
Yes.
Now, the C++ standard has two fences, which are called atomic thread fence and atomic signal fence.
Yes.
How do they map to those other ones? Like you did use the atomic thread fence, I think, as a...
Yes, well, actually,
so how do they map to each other? Like, what are the standard ones for?
Yes, so let me go back to, because the names are very close and I want to make sure that I answer correctly. Okay, so atomic, that's what I thought. Atomic signal fence, this is a compiler fence. This does not issue opcodes. Atomic thread fence issues opcodes. So like thread fence is the runtime version, signal fence is the compiler.
So they do map exactly to each other, they just have different names.
Yes, exactly. And you can see here that you can actually then also pass in a specific memory ordering. And so this actually gives access to both dimensions of that table, essentially.
All right, thank you.
Definitely, yeah.
Hi, I know we don't have time to get into multi-producer, multi-consumer.
And I was asked to make sure that you're talking into the mic so that...
All right.
Yeah, thank you.
It's not going to work. All right. I know we don't have time for multi-producer, multi-consumer, but I've seen some code where relaxed ordering is used to do a compare swap loop. Just from what you've said, I have the impression that that means the loop will still do the atomic compare swap that is intended by the loop.
Yes.
But it does not provide a fence.
So the thing that's weird here, so to be honest, I have not myself seen a platform where like a compare and swap will not issue a fence. Like basically the answer is that so again, we're talking about an abstract model here versus what the actual runtime environment can give you. And so for instance, if you did an atomic compare and swap with relaxed ordering on x86, you're still gonna get a full fence because like x86 just can't do that without it being a fence. And so the answer is that in that case, you get something stronger than what you asked for. But the abstract model with C++ is that you can imagine there might be some hypothetical infrastructure that would give you that.
Okay.
Yeah.
Thank you.
Thank you for the lecture. What about the public subscriber? Did you test it?
Sorry, say again?
Public subscriber.
Oh, well, actually, this talk, I unfortunately ran out of time. If you want to see this section, go watch the one that I gave at C++ now. But this multi-consumer broadcast queue, this I think is what you're talking about. So this is a publish subscribe model where you can have many different consumers that are all participating in the queue simultaneously. And with this one, this is what you end up getting. Like, I don't have enough time to go into it right now, but you do still end up seeing very substantial differences. And what you also find is that the false sharing problem gets magnified by having more threads in the queue, essentially. But,
Thank you.
Hey, can you go to slide 78?
yes. Okay, there we go.
Yeah, so here you, on the second licensing function, you load next producer record using acquire semantic. Do we really need that? Because we only have one writer. Like, I don't think
So
we
so you do need this. This is actually probably the most important fence in the entire, well, there's.
no,
there's
I mean the acquire log on your board.
Oh, you mean up here?
Yeah.
No, you don't need that. There was a version of this talk where I had that as like, where I was not using acquire there. I ultimately ended up deciding it just kind of confuses the issue and I wanted to make it clearer. But no, you do not need that acquire there, I
I
don't
think it
believe.
should be relaxed, should be fine.
I think in that, well, so in the original version of this talk, I also got into some places in the multi-consumer queue where I think that relaxed is also fine. But yes, I do believe that you're correct that relaxed in this case would be fine because it's just the same thread that's accessing it. But yeah, thank you. Yeah, I think so. Like, what I should say is that I know that in the testing that I did, this code works with relaxed there. But relaxed is hard to reason about. Yes.
Yeah, thanks for the help. You mentioned that the producer doesn't care about the ordering operations. I'm not sure if you mean the same way, but it kind of does, because otherwise it could override the value before the consumer is able to read it.
Yes, well, so that is true. What I mean is specifically around like ordering constraints. So let me see if I can get back to a definition of the. I have it in here somewhere. Okay, so where is pop? Okay, yeah. So what I mean here is that, so obviously within the context of the consumer thread itself, it has to do this read before it does this store. Like that has to happen that way or it's all entirely broken. But from the perspective of the producer can't really see this read happen. You know, the only thing that the producer can see is this increment into the consumer record. And so that's why I'm saying from the producer's perspective, as long as in actual fact these happened in the right order on the consumer's end, it can't see things out of order. Like it's just when the consumer has moved past the record,
Okay,
it's
so
done with the
in
record.
the sense that it can see things out of order. Yeah. makes
Yes,
sense.
exactly.
Thanks.
Yeah.
Hey, thanks for the talk. I have a question about the final bonus optimization you had there. So I think the idea you shared was that if the consumer had a cache line about the next producer index, so whenever the producer was updating its index, it's going to generate some kind of like cache coherence signal, and then it's going to invalidate the cache in the consumer.
That's correct, yes.
So I was thinking by doing this, what did you gain there? Because whenever the producer increment its index, it's still going to broadcast the signal. Like, I don't know how that works, the protocol. It's like, whoever holds this cache line, please invalidate your cache.
So that invalidation will still happen. The point is that, so the problem is that, so it will still broadcast that invalidation and its copy of the record will be invalidated on the other side. The point is that if we don't then go and read that thing, the other core is not required to like stall and fetch it, essentially. So like the idea here is that every time we update the record, it will still have invalidated that version of itself on the other side, but we are actually reading from this cache all of the time. And so the idea here is that the producer, for as long as it can, is only looking at this cache copy that it has here. This cache copy has not been invalidated. This is a separate cache line. And so the idea here is that like when the producer runs out of space, it then one time goes and loads this consumer record, and it then takes that invalidation hit, and it has to fetch it from the other side. But it then stores that back into the consumer cache, and it can then make it the whole way back around the queue before it has to look at this guy again and take another hit, essentially. And both sides do that, essentially. So the invalidation does still occur, but we don't take the penalty of that invalidation until we physically have to, because there's no more space in the
So
queue.
it's like you are more or less like coalesce all the updates from the other side, and
Yes,
then you keep
exactly.
reading that, avoiding the cache line when you try to read that until you have to, like, to get the next
Exactly,
batch updates.
exactly. And so the change here is that instead of us taking that hit on every single production, we take that hit once every time around the queue, essentially.
Okay, got it. Thank you.
Yeah.
Can you go to the slide with the fast queue pop implementation?
Okay, let me see if I can find that. This is push. Oh, so yeah. Well, all right, so that's right. This was the one. It didn't change after I did the alignment. So this is the one that does the acquire release. Yeah.
So when you start to the next consumer record, you use release semantics. So that means store will not be reordered after the release fence.
Yes.
However, the load can the like the record equals data consumer be reordered to be after the release store.
Well, so the reason that we need this fence here is to ensure that this read can't get reordered after this fence, essentially. So like what I was saying before about making sure that from the consumer's perspective, the only thing that really matters is that this read has to happen before this store. And so by doing this with release ordering, we guarantee that those two things can't get reordered.
I think that is the job of the acquire fence, right? Acquire fence store cannot be reordered after the fence, but it is release fence. So
well, so my understanding of how this works in C++ is that this is still a full fence here, in that like we can't move this load below this store here.
So the load cannot be reordered after the release fence.
That's correct. Yeah. Yeah.
Hi, thanks for the talk. I have a small question about the final optimization.
Okay.
I didn't understand why you need to put the cached values, like the producer-consumer cache, on a separate cache line.
Yeah,
as the
so
next producer record.
that I think you're also correct about. I forgot to say it earlier. So I made these slides a while ago, but I think you're correct. I think this does not have to be atomic. I think this also does not have to be cache aligned, because like the reason that I believe this is because this align as specifier here is still going to make sure that this whole other chunk is on a separate cache line. So like if this is, you could have this just be right on top of this and be 16 bytes as long as this next one is still separate. So I believe you're right. I think we could remove the atomic and the align as on the cache. Yeah.
Hey, thanks for the talk. How'd you find the paper with the original?
So the answer on that one is actually GPT. But yeah, I can. The slides will be sent out afterwards. But yes, it's. I was working with another coworker at my job, and it ended up being, I think, like a deep research thing. But
Cool, thanks.
yeah, definitely. Any other questions from anybody? Oh, actually, wait. It looks like we are getting one.
Thank you for the talk. Did you see any queues with a similar performance for multi-producer, multi-consumers?
So, and it kills me that I wasn't able to get into this. But I do have a version of this here where I talk about a version of multi-consumer. The one thing that I would say, multi-producer gets difficult because the problem is that, so one thing to keep in mind with this data structure is that at the end of the day, I was able to remove all of the read modify writes. And so like, there's no situation where I needed that lock prefix. Like with this kind of design for the producer, if you have multiple threads here, you have to then worry about multiple threads mutating that index simultaneously, and you kind of have to have a fetch add. So the answer is that at least on Intel, I do not believe that you will be able to optimize this as hard if you have a multi-producer queue. And for a work queue where the consumers are dividing all elements among each other, you're going to run into the same problem. So like it very much depends on the data structure. I chose this data structure just because, like, in my experience with a lot of lock-free data structures, it very quickly turns into like this Rube Goldberg machine that is just ridiculously complicated. And I love this because that doesn't happen with this data structure. But it's very much going to depend on the characteristics of your data structure on how, in terms of how well it will optimize. Yeah.
Thank you.
Mm-hmm.